So I also want to thank the organizers for inviting me and giving me the opportunity to present our results from Innsbruck. So thanks a lot. Let me start right away. Time is short, so my idea is that I will give you a little slower introduction, and then perhaps towards the end I have to speed up a little bit. I hope you excuse. I know that you've gotten an introduction to the world of ultra-cold atoms, in fact, yesterday already, so I can perhaps be a little bit fast on some of the things. Just want to mention I'm from Innsbruck. Innsbruck is a natural place to study systems with strong correlations. As you can see, the systems here is very strongly correlated, as Innsbruck is very strongly confined. It is, in fact, essentially one-dimensional, and it's ultra-cold. I mean, this picture could have been taken 10 days ago, and this can happen at any time of the year when the weather is sufficiently cold. So now let me start with acknowledging who did the work that I will present today. In fact, the work done was by a former student of mine who's now a postdoc in my group in collaboration with Andrew Daly and Hans-Peter Büchler from Stuttgart. Andrew Daly is now in Pittsburgh. And what will I be talking about today? I am interested in the properties of bosons and optical lattices. So think of this sketch here, and you've seen very beautiful experiments on similar systems, actually with high-resolution imaging from Stefan Kur yesterday. So what I will be focusing on today is I will be looking at systems where our coherent interaction part, let's call it U, can be of any value. In particular, it can be negative, and can depend on the various parameters of the system, in particular on the number of particles on each lattice side. So I will show you what I mean by that in a moment. So that's sort of the idea, what I will be talking about. Let me just briefly say where this comes from. What can we do? Why can we tune in an interaction parameter? And I will give you some more details in a moment. Basically, just to make that very short, if three atoms that scatter coupled to a molecular state, the scattering properties of the two atoms can be changed. And we call this a Feshbach resonance. So this is just a schematic diagram. What it means is that the scattering length, sort of the radius for the cross-section, can diverge at a specific value of the magnetic field. We tune the states via the Zeeman effect, so the control parameter in the end is a magnetic field. And basically it all boils down to such a behavior on top of some background scattering length. There is a resonance, dispersive type resonance with some width that is given by the strength of how strongly the free atom state couples to the molecular state at a specific value of the magnetic field that depends on the details of a molecular structure. So we just take this as a given fact. We have this tunability, as we call it. Yeah, scattering length is a function of the magnetic field. And in the simplest case, let me just walk back. This interaction parameter depends linearly on the scattering length. That what you would expect. Now in an experiment, I just want to show you that just briefly, without walking you through any of the details. The scattering length here in units of thousands of Bohr radii depends on the magnetic field. We have a whole series of these Feshbach resonances. I will just zoom in around this very convenient range from 0 to about 100 Gauss or so. And let me zoom in. This is the scattering length now from 0 to 150 Gauss. And what you can now see is you can see some narrow resonances. And I'm showing you this to show you basically that there's a finite number of resonances, so they're very well separated. Some higher order resonances, but basically that's it. And I'm not walking you through the quantum numbers at all. What I just want to tell you is that there's a zero crossing for the scattering length, which is well separated from all the resonances, so one can really sit essentially on that zero crossing. And I should say, usually we have, in principle, we have magnetic field control at the level of a milligauss here. So this is now 100 Gauss, so we can sit here really very precisely on one of these, let's say, zero crossings. Typically, we cool our atomic sample, called the Bose-Einstein condensate, at some specific value of the scattering length at some convenient repulsive interaction. Will not walk you through the physics of ultra-cold systems in all detail. Just want to say that this means that all the atoms sit in the ground state of our system. And but the message is we can tune interactions. We can actually tune them up along one of these Feshbach resonances. And certainly one has to compare length scales. I will not again walk you through all the details of that, but one has to compare. This is of 1,000 Bohr radii, and 1,000 Bohr radii easily compares with the confinement length in a typical confined setting. In particular, what I will also need as an analysis tool, one can use these resonances to couple to the molecular states, and one can make molecules there. So I will need that later on. So just one more ingredients that you need. Now again, so far I've talked about the elastic part of the scattering. There's also an inelastic part, which is summarized by so-called three-body recombination. And basically, sorry, I'm too quick. Basically, what it means is that inelastic processes set in, and here I'm focusing on three-body processes. So three particles combining, forming a molecule, and a free atom giving up some binding energy. And what I just want to show you here, that there are resonances, which we call Efimov resonances, because we couple to so-called three-body Efimov states. The physics of that is, for today's talk, completely irrelevant. But I just want to tell you that we have an inelastic process, a decoherence process, at a specific value of the scattering length. In this particular case, it's around minus 900 Bohr radii. So just keep that in mind, because we will need it later. It's actually something that, point is that we not only can tune the coherent interactions, but also the inelastic processes. Yeah? And you see this is actually a drastic change in this inelastic process. This is the fourth root of the three-body loss rate coefficient, and you see it really goes through the roof here if you plug in the numbers. Now, let me come back to the lattice physics, and as I said, I'm sure you have gotten a good introduction yesterday. Basically, if you look at the dynamics of particles, bosons in our case, on the lattice, the situation is the following. You have three terms. You have tunneling, interaction energy, the U that I just mentioned before, and typically some additional gentle, slowly varying trap. And one can calculate, or for cold atoms, one can calculate these rates, coherent rates, I should say. Yeah, these are all coherent processes, coherent tunneling from one side to the other, just by using Wannier functions, for example. So also the interaction we can just calculate by using Wannier functions. I should already mention here that this assumes that these Wannier functions are single particle Wannier functions, so non-interacting Wannier functions. And the external energy shift is just set by some potential. Now, what approximations does one do for this kind of system? Yeah, one first of all assumes that there are no long-range interactions. Yeah, they are only they are only on site. Yeah, when particles sit on top of each other. One assumes that there's no long-range tunneling, so this is just to the next neighbor. One assumes, in fact, for writing down this kind of Hamiltonian, one assumes that there are no higher bands considered, yeah, just the lowest Bloch band. And also one just assumes that the interaction is just contact, and just writes down a delta function type of interaction. And here you see the dependence, the linear dependence of U on the scattering length A. So this is very simple in principle, and certainly one has to make a lot of approximations. Let me just remind you of what then the system does when one does that, when one takes all this for granted. For sufficiently large tunneling, the system is delocalized. It is superfluid in the lattice, and it is it's all coherent. And if one lets interactions dominate, the system is a system of localized particles. It in particular shows so no phase coherence. One would not expect any interference patterns, and the system then has a gap that is on the order of U. Now, and this has been much discussed over the last 10 years in the context of cold atoms. One then expects this kind of phase diagram, the superfluid phase here as a function. So what's plotted here, I should perhaps back up a little bit. So this is a chemical potential, and this is a tunneling strength here. And if one reduces the tunneling strength or increases interactions, one enters into this localized phase, which depending on the chemical potential or the density of the system, can have 1 particle per site or 2 particles per site, and so on. And in the experiment with a harmonic confinement, one would see in one trap, one would see that all at the same time. One would get a wedding cake structure, and I'm sure I I wasn't there yesterday, but you showed all this in situ in very nice pictures that one can actually measure that directly, and the list of groups that have been working on this is getting longer and longer. Now, the experimental setup is such that we do this in a 3D setting. We shine in laser beams to generate the potentials via optical dipole forces. We can control all these parameters in principle independently. Just to remind you, the tunneling rate we control by the depth of the potential, the scattering length controls the interaction, and some external dipole trap to some extent also controls that external potential. Now, how does one probe that? And there are various ways, and one of the standard techniques is actually to go into this, localized phase by changing the depth of the lattice and then seeing how the coherence of the system disappears. So that's basically shown here in time-of-flight images. And I'm sure you've seen that before, so I don't have to walk you through that. Let me just to warm up show you what we do. We look at one of these time-of-flight images. So this is the system is still superfluid. The pattern looks like that because we look at it from some funny angle. That's irrelevant for what I will be talking about today. Just look at the width of this coherent peak here at the center, and that's what we plot as a function of the lattice depth, the width of that peak, as we increase interaction, as we increase the lattice depth for a different strength of the interaction. So we just dial in our scattering length value, and then we just go through this phase transition. And basically what we see is that this width has basically stays constant for some time and then increases drastically, and we associate the phase transition with this kink in this curve here. As you would expect for strong interactions, the localization happens quicker, so this kink happens earlier as one varies the lattice depth. One can plot that as a function, this phase transition kink point as a function of scattering length, and it actually turns out that basically it depends a little bit how you define where this kink is. I mean, turns out this is somewhat difficult to really determine where you really would determine this kink to be, but it basically agrees with various theories that are able to calculate that phase transition point. In fact, Monte Carlo simulations or mean field calculations. So this is a reasonable agreement. So this is just a warm-up to show you that we basically think we understand this phase transition. Now, let's do further analysis of the phase transition. One can look at the Mott insulator excitation spectrum. What does that mean? One excites the system by modulation techniques, I'll show you in a moment, and basically one then moves particles on top of each other and has to pay a price in energy for that. And what would one expect naively? One would expect, well, for example, if you move a particle from here to here, you have to pay the price of this energy U, or if you move a particle to where you have already two particles sitting, you have to pay the price of 2U. In this case, you have to pay the price of U, 2U, but you get the price of 1U, so in difference is U. So you would expect peaks at U in the excitation spectrum and at 2U when you excite, in fact, between the shells. So if you do excitations here between the 1-atom Mott shell and the 1-atom Mott shell and the 2-atom Mott shell. The technique is modulation, amplitude modulation. This has been well established. In fact, Henning here worked on this, was one of the pioneers with the Esslinger group many years ago, doing these techniques over many years in various contexts. So basically, let me just remind you of how this works. We take our sample, which is a Bose-Einstein condensate at some value of the interaction parameter. We then ramp up the lattice. We then usually at that point then we change interactions to some specific value, then we modulate, and then we go back and we recapture the system, and we then look at the condensate fraction. Basically, we heat the system during this process because we cause defects, and our one way of measuring that is just looking at how much of the condensate is left over. Yeah, so one looks at either the thermal or the non-condensed fraction and the condensed fraction. And in the experiments, basically spatially, this is just the sort of the non-condensed part that's spatially separate in these measurements. It's time of flight measurements. So now, how does it look like? A typical experiment. So we measure this fraction as a function of the modulation frequency, and what you can see clear resonances. In fact, I showed you that, and was too quick. And in fact, this is the U resonance for our specific values. It's at 1 kilohertz, and this is a 2U resonance, which is then at about 2 kilohertz. Now, this is at considerably weak interactions. Now let's increase interactions, and here for about 320 Bohr radii now. And now, interestingly, what happens is that this U peak starts to become asymmetric and, in fact, develop some side lobe. And if one increases that further, let's move into that peak. Then this double structure completely splits. Yeah. So these are 3 curves for different densities that I will walk you through in a moment. But you see a very strong splitting now of this peak, which for strong interactions by now has shifted to 2 kilohertz. Now this has shifted certainly because we have increased the scattering length here. But it's now it's 2 different peaks. So now what is happening here? Well, I said earlier some approximations have been made for the simple theory. In particular, assuming that we only take the lowest Bloch band, that we just take a simple approximation for the interaction potential. And that's not valid for strong interactions. And that has been discussed in the literature over the last 10 years, or even more so, particularly by Thomas Busch and collaborators many years ago. This is what happens for the energy of the bound states, and just taking just 2 particles in a well. This dashed line, without walking you through the details, is the Bose-Hubbard, what you would need for the Bose-Hubbard model, but you see this modifications due to the trap structure. So this is, you would expect, yeah, for 2 particles, and one has to take the right delta function potential, actually, one has to regularize it. And then the next step is actually one has to watch the situation, what happens when 3 particles are present, yeah. They change, actually these particles interact, and the density is changed, and so effectively this means one has effective free-body interactions that shift the energy of the system. And this has been discussed some years ago in this publication. And last but not least, just to make a little connection, because that will be the future. If I have 1 minute later on, I will show you that. One also has to really take into account the 3-body bound state that might appear at some point, in particular for attractive interactions. Yeah. But this, in fact, for the lattice work is work in progress. So, but let's see what happens. Yeah. In this Bose-Hubbard model. And so what one generally would expect is that this U now depends on the number of particles. Yeah. So it's not independent of how many particles one has at each side. And naively you would expect that, because if particles actually do interact, you cannot simply take non-interacting functions, one-year functions that describe the dynamics at each side. Yeah. The repulsive interaction or attractive interaction would lead to a shift in energy. So, so now one can go back and then say, well, okay, we have a process here that depends now on 2 particles. But now if one does a process like that, or let's say, as an example, take this one, yeah, one takes away 2U that depend on 2 particles at each side, yeah, and but has to pay the price of 3U with 3 particles. Each of these particles interact with each other, yeah. So that would be now the right energy that one has to calculate, yeah. So, and in fact, one can probe that because I said, well, these processes happen at higher density. So in the 2-atom short shell, these happen at lower density. In fact, that's what we do. We test for low densities. Yeah, low densities in our case means we have essentially just a 1-atom Mott shell. We almost have no occupation in the 2-atom Mott shell. Unfortunately, we cannot look at it in situ. We don't know exactly, but we can certainly test that. And show you actually how in a moment. And for high densities in particular, we see that both of these different peaks appear. So these are the 2 peaks that appear in this particular case. Now, one technique, there are 2 ways of probing all this. One technique is actually looking at double occupancy by turning the doubly occupied sites, yeah, for example, a site like this, into a molecule. Yeah, so this would be a molecular peak here. Yeah, and one can look at triply occupied sites by looking at loss. So in fact, we see then on this particular resonance, where we have triply occupied sites, we in fact see a 3-body loss, which we don't see on the other resonance, because there are no 3 particles on each side. So, okay, without going through all the details of the theory, That's the expectation here, and our data. Sorry, too quick. The dashed lines are the Bose-Hubbard, the simple Bose-Hubbard correction. It turns out this is the splitting that I just showed you here, so this is actually quite sizable. Splitting is very large. It's on the order up to a kilohertz or so. And it turns out this, just as one comment on the theory is a perturbative theory, and it turns out if it's actually not known how to sum up that series. And if one does some assumptions, one can try summing up the theory, and then the red line appears. The dashed line would be that what the theory says. So in fact, it turns out that this three-body process is in detail not understood yet. It's a sort of an educated guess of what's happening here. And you'll see, and I'll show you in a moment, we see deviations from that, when those two attractive interactions. And I should mention there's been nice work from Emanuel Bloch's group some years back, where actually this splitting was seen down here at about 100 Bohr radii in sort of beat measurements with this Mott insulator state. Yeah. So, but this effect now is much more drastic because we can tune the interactions to much larger values. Should mention the typical experiments are done with rubidium, and the scattering length is about 100 Bohr radii. Now for the last few minutes, let me switch now to the attractive case. Yeah. So this actually was in that sense a warm up. So with the attractive case, three-body loss plays a role, as I showed you earlier, this huge Efimov resonance. So what happens if one goes through that resonance? One would expect naively, at least in free space, one would expect the three-body loss characterized by this rate. And in general, if one goes into attractive interactions, one would not expect that the superfluid is stable. Yeah, it should collapse. Yeah, and in the end, it will decay due to three-body loss. And the ground state, even in the Mott insulator case, would be basically all particles sitting on top of each other, which is ridiculous, certainly, because they undergo this molecular process. So now, certainly, what we can do is we can first go into the repulsive case and then into the attractive case, and then ask ourselves how stable is this Mott insulator state? Yeah, is it for attractive interaction? Has it some stability, or does it decay immediately? And it's for sure not the ground state anymore, yeah, because one now has attractive interactions, and that would be the ground state of the system. Now, how do we do this in the experiment? We load the lattice to a certain depth with repulsive interactions indicated in red. Then we switch to attractive interactions. We go through the zero crossing and go to attractive interactions. The system certainly is frozen over that time scale. Yeah, I mean, at this depth of the lattice, the tunneling rate is not zero. Yeah, so the tunneling rate has still the time constant on the order of 100 milliseconds. So you'll see that in a moment. And then you can either leave the system, or you can again use modulation techniques to see what happens. And then we can measure, as before, the excitations that we introduce into the system, and observe overall heating of the system when we go back to the repulsive case. That's the way of doing it. So let me show you data. Basically, what we do is the following. We just vary the interactions. We start, as I said, with the repulsive case, and then switch to the attractive case. And you see we are quite attractive here, up to a few thousand Bohr radii. We see that something happens. First of all, there are some narrow resonances I showed you earlier, which are irrelevant for today's work, but they are a little bit nasty. If we hit one of these, it's a problem. Okay, we can discard those. There's a zero crossing here that because we course it with a finite speed, it causes some problem. Yeah, the system becomes briefly superfluid. Yeah, and it seems to. So we see that we always seem to lose particles, and in particular we seem to lose BEC fraction here. So this is again the BEC fraction. But now we can just sit here at some attractive value and see how long the system lives. And you would now say, for the given value of the depth, the system should decay on the time scale of, let's say, 1/10 of a second. And it turns out it's not the case. It decays on the time scale of seconds. Yeah. Actually, the time scale here is about 15 seconds. Yeah. For even very attractive interactions. So for sure, there's a blockade effect. And it's probably two things. It's the fact that you have very strong repulsive interactions, attractive interactions actually also lead to a blocking of particles moving to a site where they can be lost, and one has actually this dissipative process that does something. I come to that in a moment. Just to make that data a little bit more complete, we also plot atom number as a function of scattering length. Yeah, so we do lose some atoms here, so there's some loss happening, and Okay, perhaps we are not fully in the Mott insulator state, completely, perfectly, and so on and so on. There's some defects. Nevertheless, the system is is even more stable, certainly with respect to atom number. The time scale is somewhat longer. You see up to 10 seconds here. So we for sure lose coherence faster than we lose particles. Okay, anyways, we do the same measurements as before. We do the same resonances. It's the same technique as before. We can look again at the pair production, or the doublon, if you wish, creation efficiency with turning pairs into molecules. So we see 3-body loss resonances and 2-body enhancement here. So we can analyze these resonances again for different densities. And it's again similar processes as before, as you would expect. We can take a whole series of these kind of spectra for different attractive interactions now. So this gray part here is this 2-body resonance. The the red part is the 3-body resonance. And for the last few minutes, I will focus on that. And there's in fact a resonance coming down from a higher band, yeah, on which I will not talk about today. It has to do with higher, especially excited states, yeah, band structure. So now this is the upshot. I showed you this data already before, the splitting here. For the repulsive case. Now let's go to the attractive case. Here the theory fits much less. We don't know why, admittedly. Yeah, could be several reasons. We do not think that we have a problem with the calibration of the scattering length. That's not the problem. We think the theory even the 2-body physics it misses. Yeah. Now, but for now, I just will stick with the 3-body problem here. So the 3-body resonance. It turns out this resonance here, what's happening with that? Again, the theory, even that educated guess doesn't fit anymore. And this resonance here shows some funny behavior. I'll show you that. This is the resonance here, yeah, the real data. It shifts as expected. It has to shift, yeah. It turns out it disappears. It broadens, yeah. In fact, what we think is happening, there's 3-body loss, as I mentioned before. Yeah, this is the 3-body resonance. And the stronger the loss, so we really are moving up towards this resonance here now, this Efimov resonance. We are way away from the top yet, yeah. We are still at 400 Bohr radii, which is about here. But this 3-body loss is setting in. And what we think is happening is that, in fact, this big loss here is blocking the coherent processes. Yeah. So, in fact, it blocks itself out of existence. So, what's the analogy? It's actually known as the Zeno effect. If you have a 3-level system, some excited state, some states coupled to an excited state with some coherent coupling, and you have a loss process from that, you can ask yourself the question, what is the effective loss from here to there? Yeah? And I'm sure many of you have seen that. And the calculation is trivial to calculate that effective loss rate, yeah, given some detuning here. What's the analogy in our system? In our system, the analogy is atoms at these wells coupled via the coherent tunneling. The loss is a 3-body loss. And the process is then these particles get lost here. So what's the effective rate? And one can do these associations. Particular J is equal to omega here. And the detuning corresponds to the coherent evolution. And for sufficiently large 3-body loss, it should look like that. Yeah. So you have this very characteristic suppression, well known for anybody who has looked at the Zeno effect, that it squares with J is J squared over the old loss rate. Yeah. So you see that large 3-body loss should stabilize the system. So one can look at these widths of these resonances, yeah, that I just showed you before. Sorry, let me just go back. Of this resonance here, yeah. One can plot that. We don't have a theory of how it should look like for the attractive case. So if we go more and more attractive, this width increases. It becomes hard to measure a width because it gets so broad, yeah, that it disappears, yeah. We can also look for the repulsive case. The increase here is not so drastic because we don't have this enhancement near this Efimov resonance. It would be nice to understand the details of that. So I'm just showing you this very general data. Now, the last 2 minutes, let me ask you what could happen. Yeah? Now, we have a process like this where we have, let's say, doublons. Yeah? Not molecules, just pairs. Yeah? And they move in this lattice. Yeah? The question is, could that be stable for attractive interactions? Yeah. And in fact, it should not. Again, when this particle moves here, this doublon particle moves. 4 particles is already 3 and more, and you have again a 3-body loss process. So that also should be blocked. Yeah. So you could certainly have a process like that where there's an empty site. So the question is, could that system be stable? And in fact, Andrew Daly, a few years from Innsbruck, suggested that one could have a very interesting system that would have not a Mott insulator of dimers, but for the attractive case, one would have a superfluid of these doublons. Yeah, so there would be a very peculiar state because it's not the ground state, it's a highly excited state, but it could be superfluid and it could be stable due to this quantum Zeno effect. And that's actually the ongoing work. How do we prepare that? How do we prepare such a system? We start with a one-atom Mott insulator state, so I can only show these pictures. Stefan, sorry, don't look at this. Yeah, I can only do a comic, yeah, because we can see in situ these pictures, but for what I will show you, it's at the moment irrelevant. What we actually do now, we create doublons in a very, very nice trick where we tilt the lattice briefly and tilt it back. Yeah. This is known as quantum magnetism. Just recently, this was pioneered in the Greiner group, that one just has one particle move to the side. Imagine you tilt along one of these directions, forget about the dynamics transversally, just along one direction. And each of these 1D systems is independent, and one creates then this kind of situation where one has a spin up, spin down, spin up, spin down, this pseudo-magnetic state. In fact, we can do that in the experiment, and that would be our starting state. Yeah? Let me just show you that we are working on this right now. This doublon creation works very well. Yeah, this is the energy shift, the tilt that we've introduced for different interaction strength, and we see that the singly occupied sites we initially have about, in this case, about 70,000 atoms in a one-atom Mott shell. Actually gets drastically reduced. Yeah. And the two doubly occupied sites get strongly enhanced for various values of the interactions. If you have weaker interactions, you expect the tilt to induce that transition first, quicker. Yeah. So this is just the raw data, very, very preliminary. If one puts in numbers, it turns out we can turn 75% of our atoms into doublons. And the question is, what's the limit? Yeah, can it be? I mean, basically. We should be able, apart from the tiny superfluid fraction that's around the one-atom Mott shell, we should be able to turn all of that into doublons. Yeah. So, and that would allow us to then look at the dynamics of such a system and see whether this is blocked or not. Yeah. So, my time's up. I'll stop here. I will not go into. But I know some of you that I would like to talk to about now what happens with these Efimov resonances in the context of the lattice. In fact, we have a lot of data that we don't understand. But I want to stop here, and thank you for your attention.